All right, I think we'll get started. Howdy, I'm Victoria Schmidt from the T Smart Grid Center, and I'd like to thank you for joining us today for the Smart Grid Center webinar titled An Extensible Approach for Modeling the Impact of Deterministic and Stoic External Impacts in the Power Flow and Contingency Analysis. If you have any questions during today's presentation, please send them via the Q&A feature at any time. We'll do our best to answer as many questions as possible at the end of the presentation. Today's presenter is Dr. Thomas Overbye, who is the director of the Smart Grid Center, holder of the O'Donnell Foundation Chair 3 professorship in the Department of Electrical and Computer Engineering at Texas A&M University, and Section 6 chair of the U.S. National Academy of Engineering. Prior to joining Texas A&M in 2017, he was a professor at the University of Illinois at Urbana-Champaign. Before starting his academic career, Dr. Overbye worked as an operations engineer for Madison Gas and Electric. He is the original developer of Power World Simulator, the co-founder of Power World Corporation, and has extensive experience in many aspects of electric power systems, including participation in and leading numerous large-scale electric grid studies. Moreover, Dr. Overbye is a passionate educator, co-author of a widely used power system analysis and design textbook, and has received numerous awards for research and teaching from both academic institutions and the IEEE Power and Energy Society. Dr. Overbye, take it away.
Okay, thanks, Victoria. Today I want to talk about how we can take some of our existing modeling that we've been doing to represent external inputs in the power flow and also include stochastic models. That's what I'm going to tell you. What we'll be working on is primarily the power flow, but what I do with the power flow, I could also do with the optimal power flow as well. In the talk, I'm going to use the term external inputs to represent, and I'll refer to them as EXIs, as inputs into the power flow from external events that change power flow parameters. And this could be things like the wind speed at a location changing how much power a wind turbine generator could make, the amount of solar radiance coming in to change the solar output, or temperatures on lines changing their ratings, or what we'll be talking about a lot today are earthquakes taking out power system components. Okay, so I should say that these slides contain contributions from a number of people, including my students here at Texas A&M, postdocs and staff, and also from Power World Corporation. Some of the work that's presented here is associated with a DOE project that we are doing, and we greatly appreciate the support of the U.S. Department of Energy for this. Okay, before I get into the presentation, I did just want to give a little shout out to some things that we have coming up here at Texas A&M. Next week, we've got a short course on an introduction to artificial intelligence and power systems. Jonathan Snodgrass, who is one of the people in the Smart Grid Center, is going to be leading that course. And if you're still interested in signing up, there is space available. We'll be doing an online short course on geomagnetic disturbances. We just had to move it from April to May, so it's going to be May 19th and 20th. And then also for those of you who are in the area, we will be having our annual research day at the Center for Infrastructure Renewal in Bryan, Texas on April 27th. And if you'd like to sign up for that, I've got the details given on the website below there. Before getting in my presentation, I did have to mention that hopefully within 2 hours, we're going to be sending people back to the moon for the first time since 1972 with the Artemis 2 mission. This mission got postponed and it ended up being on the same day as my webinar. So I was like, oh, I hope it's not at the same time as I'm doing my webinar. Luckily, they're launching hopefully at 5:24 p.m. Central Time tonight. As somebody who grew up during the Apollo era, this is a big deal for me. When I was a kid, I watched all of the moon shots, all the Apollo shots, and I particularly remember Apollo 8 because that was the first time people went around the moon. And since I grew up by Milwaukee, it was a really big deal in Wisconsin because we had our astronaut, James Lovell, on Apollo 8. They were the ones that took the first Earthrise picture, which I've got posted there. Of course, Jim Lovell got to be more famous with Apollo 13 because, of course, of the failure with Apollo 13. But before that, he was on Apollo 8. Okay, so we hope that mission goes well. Okay, so this presentation has a lot of material that we have been developing for a DOE project. The project is focused on dealing with natural hazards impact on the electric grid, and we are also extending some planning software to allow integration with large language models. The goal is to make better planning software that can deal with these more extreme resiliency events. It's got a 2-year R&D phase, which we are currently at the beginning of, and then we're going to be doing a demonstration at several utility sites in the 3rd year. This project involves us here at Texas A&M University, people at Power World Corporation, and then a consulting firm called Grid Focus. Okay, so that's the project team members. The reason why I put it on is we have project team members, of course, from electrical and computer engineering, power systems people, but we also have people from mechanical engineering, atmospheric science, civil and environmental engineering, because we're trying to model the impact of external events such as earthquakes or more extreme weather on the grid. So we're tapping the expertise that we have here on campus to develop good models for those things, and then take that information and bring it into a power flow so that planners can use it. This project is helped by having Power World Corporation involved with it because that means that results can be directly implemented in planning software and kind of transferred to industry pretty quickly. And then Grid Focus has some consultants who have good experience in the utility planning space. The project has a number of different tracks. The one that I'm going to talk about mostly today is the modification of power system planning tools, and primarily, I mean Power World Simulator, to directly incorporate the effects of external inputs. And I'll be unpacking that as we go through the presentation. It's also going to talk about developing scenarios for these natural hazards, and then a little bit on the synthetic grids, not too much on the large language models, although we expect to have another SGC webinar on that in the next couple of months. Okay, so what's the motivation for this? Motivation is power systems have always depended on external inputs. Certainly, one big external input is the weather. Human activity depends on the weather, so that means the electric load depends on the weather. And increasingly, more and more power system parameters depend on the weather, particularly as we integrate in all this wind and solar generation. Currently in the US, we get about 19% of our electric energy from these sources. And that means that a lot of our generation is weather dependent. If the wind's blowing, then you have high max megawatt values. And if it's not blowing, they're lower. Other ones, like, we're all looking at trying to get more capacity out of the transmission grid by using ambient adjusted line ratings or dynamic ratings on the lines. So that's something that these inputs could handle. And then there's more concern about the big risks to the grid. One of the risks that I'll be talking about today is earthquakes. Okay, this is just the definition of planning. What I am primarily talking about today is focused on planning, although some aspects of it could be certainly used for real-time operations as well. Planning is forward looking. So what you try to do is you try to leverage historical information and then use forecasts of various things, including what the load is going to be and any potential hazards that we're going to run into, and then try to get the grid set up to be able to meet the load as effectively as possible. In doing planning, of course, you have to deal with lots of resiliency considerations. Um, Certainly, we've dealt with weather for quite a while. In fact, when I was an undergrad at University of Wisconsin-Madison, my senior design thesis, or not a thesis, my senior design project was bringing weather information into the Madison Gas and Electric Control Center. So I would read data coming off of a teletype, and we'd send it over to the control center for use there. So weather, I know weather's been used in control centers for a long time, but we want to get it more directly involved in the planning process. And then there's other extreme events, hurricanes, ice storms, derechos, tornadoes, um, eclipses, which we had a couple of years ago, and earthquakes. And as I mentioned, I'm going to talk about these as external inputs, abbreviated in the slides as EXIs. Okay, so what are risks that we have to deal with in the electric grid? There's lots of different ones. A couple of years back, I got to be on a National Academies committee that looked at enhancing the resilience of the nation's electricity system. And one of the things we did was to try to identify what are the risks to the grid, what are the categories. So figure 3.1 in that report gives you some of the categories of risk. Certainly, it doesn't list all of them, but I think it lists the major ones. In setting up the graphic, we decided we would have the x-axis be the amount of warning time before the event, and then the y-axis be the time to restore service after the event. Some events they occur suddenly and they're over very quickly from an event itself point of view, and an earthquake is an example of that. On the other side, a drought is something that can develop, or a drought is something that develops over a longer period of time, and then it could take quite a while to come back from the drought. If you're interested in that report, it's available for free. Just go to the address I've given there. Okay, so to use weather and these other external inputs in the power flow, we really need three things. And most of what I'm going to talk about are the second and the third one. The first thing that you need geographic information on your electric grid components. This is something that thankfully in recent years has become much more available. Nowadays, it's very common that when you have a power flow model, you either have in the model information about the geographic location of the substations, or you can get that information fairly readily. The second one is you need access to data sets that tell you what these external inputs are. Uh, with weather, there is a lot of data available, and I'll show you some ways that you can get access to weather information. And what we're working on is trying to develop other sets for other sorts of events and make them readily available. Then the third is how do you model the impact of these EXIs on electric grid components? What we'll see is the impacts can be either deterministic or stochastic. And a lot of this presentation is focused on dealing with stochastic models. Okay, so talked about that. The background on this is a couple years back, probably 6 or 7 now. We were doing a project for ARPA-E, and we were developing synthetic electric grids. And associated with these synthetic electric grids, we needed scenarios. For example, it was a dark and stormy night. So that electric grid might represent a storm condition at night. And we had a lot of renewable generation in these grids. So we had to set the outputs of the generators. And we wanted, of course, to do that consistently. If it was dark, if we had a nighttime scenario, then we shouldn't be having any solar generation. Or, if it's a windy day, then we had to figure out, well, what should our wind generation be? rather than coming up with fake scenarios, what we decided to do is, since our grids were geographically based, that we would just go out and get historic weather information and then use that weather information to set our inputs. The second motivation was a couple of years back, it started in 2020. We did a project for Southwest Power Pool in which we looked at an AC interconnection in the eastern and western grid. And then a couple of years later, we expanded that work to look at the economic implications of such a connection. And in doing that, we again needed a lot of information about what the renewable generation was doing. And that was easiest to set if we had actual weather information. Okay, so rather than trying to synthesize this, we just got actual weather data and have been using that ever since. Where do you get this information? We started out just getting weather information from the station measurements, like airports, and then in talking with folks here in atmospheric science, they said, a good other set is to use reanalysis data. So since then, we've kind of been using reanalysis data, which are outputs of models that are either forecast models or they take a model and combine it with historical information, sort of like a state estimation for weather information. A nice report on weather system data needs in planning and power systems is the one I've listed here that came out. It's by the Energy Systems Integration Group. It came out in October of 2023. In that report, they mention a number of different data sets that are used that you can use to get weather. We've been doing a lot of work primarily with the second and third one with the ERA 5 data and the HER data, and I'll mention that briefly. Though most of this presentation is on stochastic models associated with earthquakes, but certainly weather plays a big role in this sort of work. Okay. That's just some visualizations of weather information that we can do in Power World Simulator. The one on the left is wind speed coming out of ERA 5. ERA 5 is a data set that has good data worldwide going back to 1940, but it's only on a 0.25 degree grid. The other one on the right is HER data. HER stands for high resolution rapid refresh data that is for the CONUS part, the contiguous US, and it's 3 kilometer grid data. So it's got a much higher resolution. Okay, so we do make it easy for you to get access to weather information. At Texas A&M, we have a website where we put out weather data in a public format. It's a PWW file format, power weather format files, and then we make them available. We've got data from ERA 5 going back to 1940, and then we also have some of the more recent HER data. Okay, and that's just the website if you're interested in getting access to the data. Okay, most of the presentation then is going to be on expanding this methodology to deal with stochastic models. So one of the stochastic models that we deal with are earthquakes. And earthquakes, of course, can wreak havoc on the electric grid. We saw an example on the western grid where an earthquake in I believe Southern California or California at least ended up splitting the WCC because of the generator outages. This is a map that we got data from the website given below there, and now Power World can load up this data. This data is on a 0.05 degree grid, and what's shown in the contour there is the earthquake value that is most important. I talked to one of our folks in our civil engineering department, and she told me that the key parameter you want to use with earthquake risk is peak ground acceleration, PGA, and then PGA, since it's an acceleration value, it's expressed in terms of gravity. So a PGA of 1 means that the earthquake is causing motion equivalent to what you would get with gravity, so 9.81 meters per second squared. This is a map of the risk of the US, and the examples I'm going to do focus in on the kind of bullseye there in the southeast Missouri, and we'll be using that data for some of the simulations that come up. Okay, that graphic there has 611,000 data points in it. Okay, so the focus here is not really on the EXIs per se, but it's their impact on the power grid. So to represent this, as we got into this work, we realized that there would be quite a number of these models that would take a mapping between some external input and then some power system component. So we developed a modeling methodology that we call PFW models. They originally stood for power flow weather models, and now they stand for power flow whatever models because they can handle pretty much any type of input, and then they can handle impacting pretty much any power system uh, value. There's two classes of these. There's the deterministic ones and there's the stochastic ones. And as we got started on this work, we dealt with the deterministic ones. Whether, the output of a wind turbine is a deterministic one in that you can say for a particular wind speed at the hub height is going to produce this maximum power output. Uh, that's deterministic. The stochastic ones use some random variables to represent probabilities for the output. So that is going to be the focus on the presentation here. So I've got a model in which the model embeds within it at least one random variable. Okay, so this is an example of a deterministic one. We've had this for a number of years. The PFW model is just saying for the input, I take wind speed in some parameters, say meter or some units, say meters per second, and then my output is how much maximum power can that unit deliver, normalized in the figure there. Okay, and we can represent these. Most of our models use a piecewise linear representation, but you can use other representations as well. So you would supply the data on the curve there, and we've got some generic curves set up as well. Okay, the second type is the determinist or the stochastic ones. And in a stochastic PFW model, an example would be a fragility curve. And with a fragility curve, the x-axis again has some external input. In the example on the left there, the input is peak ground acceleration expressed in units of gravity. And then the y-axis is the probability of failure. If this, in this case, it's a transformer, were to experience the specified PGA, the y value tells you the probability of failure. And in the first example, I'm going to assume the PGA is 0.5. So if you look at the intersection here, it says it has a probability of failure of 0.5. So that means that if that transformer were to experience an earthquake with this maximum ground acceleration, its likelihood of failure is 50%. So we've got it so that you can set up in a power flow model a PGA, a PFW model, and you can have lots of different models here. And then for that model, you would have to enter in its parameters. Okay, when I talk about this, people will say, well, where do you get this data from? And the good thing is there's lots of sources in the literature for various data sets. So the PFW models that we're dealing with, usually we are not creating the input data. Rather, we're just setting up a way that somebody can enter that input data and in particular units and map it to associated power system components. As we got into fragility curves, EPRI has a really nice report. It came out in April of 25, fragility curves for quantifying physical climate risk in the electric power sector. It's a free document, so you can just go out there and get it from the website I've given there. And it tells you about modeling fragility curves for different power system components. And this is an example of one of the fragility curves there and how they're getting the data. Here they're taking kind of historical data saying, well, what happened to, in this case, it's I believe it's towers, transmission distribution towers, and the data says how likely during this storm were our towers to fail, and it became dependent on the 3-second wind gusts. And wind gusts are something that we have in some of our weather data sets. And then they derived a curve from that that told the probability of failure. If you read the document, they do mention something called a hazard curve. Hazard curves are different from fragility curve. A hazard curve is used to tell the probability of some external event exceeding a particular value within a specified time period. And usually those are plotted on a log scale. So this is, I guess there's some overlap there, but frequency of exceedance, how likely is something to occur? Here, the intensity is a 3-second wind gust. Of course, we always get small wind gusts, but as you get into higher wind gusts, they tend to drop off on the scale shown there. I guess it's a log linear scale. If you want some additional data, EPRI's got a nice inventory of fragility curves. You can go out there and they list various fragility curves and then an associated citation, and you get more data on the curves from there. The takeaway from this is there's lots of different fragility curves in the literature. Of course, as you're applying it to your system, you have to use, you have to modify the model. The model might just be a piecewise linear curve, and then you have to set those parameters depending upon your particular piece of equipment. Okay, so in doing this, we wanted to make it easy to set up a modeling methodology for these PFWs. And in coding it up, what we realized is that we really already had code for doing this. And the code that we had was what we used in the Power World code for stability models. And stability models have been around since the first stability codes came out in the early 60s. And the idea on that is you attach different models to different devices. You might have a machine model, an exciter model, a governor model, a relay model, and then you code it up so that you have different classes of models. For a machine model, you might have a classical one, you might have a Gen RU model, you might have a Gen TPF model or something like that. And it's a straightforward, well-known, kind of well-documented methodology. The PFW models fit this same methodology. So actually, a lot of the code that's used for modeling stability models can be used with PFW models. This is just an example. When we were doing the SPP project, we had a combined east-west grid. And in that east-west grid, we had about 250 different types of stability models. I've listed some here. There are different DC line models, a bunch of different exciter models, and about 100 or about 66,000 different stability model instances. So the code is set up to handle lots of models, be they stability models or now PFW models. We've got ways set up to make it easy to enter large numbers of PFW models. Coming up, I'm going to show you an example with a 1,000 bus case in which I put PFW models, fragility models on all the transformers, And I just kind of pasted that in very quickly. Okay, so how do we deal with a stochastic model in the power flow? Dealing with uncertainty in the power flow is nothing new, and that's something that we have been dealing with throughout the history of the power industry, at least since we started using digital power flows and probably with network analyzers before that. The two common approaches are either you develop a stochastic power flow, and if you look in the literature, the first stochastic power flows were proposed about 50 years ago, or you go with the Monte Carlo approach. Um, the Monte Carlo approach is where you just do a whole bunch of deterministic power flows. In implementing this, we decided that we would handle stochastic PFW models using the Monte Carlo approach. The reasons were, one is it's got good conceptual simplicity. Two is it's able to incorporate complex modeling features. And three, its ability to handle stress cases, including non-convergence. So if you are unfamiliar with Monte Carlo, it is a widely used modeling methodology. The classic paper in this area actually dates to 1953. It was written by some people at Los Alamos lab primarily, and it has been used in the power flow for at least 70 years, I would guess. Um, there are many books and papers on the Monte Carlo method. The focus here isn't to get into the details of the Monte Carlo method, but rather to show how it can be easily implemented in existing power flow simulator here. And the solution that we came up with is we would just extend the existing contingency analysis application to let it do to let it easily do Monte Carlo simulations. So contingency analysis is, again, another widely used power system modeling application, probably dates back 50 years at least. When I was looking for early papers on it, they go back at least 50 years. And the idea is contingency analysis is you just process a whole bunch of power flows, and between each one, you go back to the base power flow, and each contingency takes out some devices or does something. And when I was undergrad in my power system analysis class, I was actually doing power flows using cards. And I would do contingency analysis on my little 5-bus power system with my cards, but just removing the card associated with a particular line. And that resulted in the line outage. Of course, a lot has been done since then. And when I was talking to Jamie Weber at Power World about what all goes on in a commercial contingency analysis, he said a lot. And this is an application that has been developed over many years. So it's got a lot of functionality, like it's got embedded logic on relay actions. You've got support for remedial action schemes, modeling generator voltage control, dynamically determining which breakers to open to isolate devices, and lots of other functionality, including parallel processing support, result reporting, and visualization. So by leveraging contingency analysis to do Monte Carlo simulations, we immediately got all this functionality. So the approach that has been implemented here and is being used on this project and is implemented in PowerWorld's code is you set up a bunch of primarily empty contingencies, and the auto insert contingency dialog has been modified to do this. Maybe you want to insert 100 blank contingencies or 500 blank contingencies. And then there's functionality to allow the stochastic PFW models to be applied to each contingency. And then you run contingency analysis as normal, and you can take advantage of all its capabilities to interpret the results. So to give you an example of this, let's consider this 37 bus case here. It's got a 345, 138, 69 kV grid, and it's got 14 transformers in it. Let's assume that all the transformers are in a seismic zone in which the 50-year 10% likelihood of exceedance of PGA G is 0.5. So we're going to model the response of this grid to that sort of earthquake. So we're going to assume that at all locations in the system, there is a zero point 0.5 uh, earthquake. So that's the acceleration that these transformers experience. Each of the transformers is modeled using the PFW model that I mentioned earlier. And I pointed out that at zero point 0.5, the probability of failure is 50%. So as I go through the contingency analysis, what is going on is it is applying this curve to each one of the transformers, and then it's setting up random variables to determine whether that particular transformer has failed or not. So this is my environmental input. I just set up a grid where the PGAG value is zero point 0.5 everywhere. And then the PFW models are set up for each of the transformers. They're identical. And at zero point 0.5 on the x-axis, that corresponds to 50% probability of failure. So then they are set up in contingency analysis, and the only thing that you have to do is just tell contingency analysis to include the stochastic PFW models. If you insert blank contingencies, this is set automatically. The default is false because, or don't include them because we don't want regular contingencies suddenly having to deal with a whole bunch of stochastic inputs. And then as you go through each contingency, it is setting up dynamically the elements in that contingency. And this column here tells the number of models that were opened in that contingency. The first one opened 7 transformers, the next one 5, 6, 6, 8, 7, 4, and so on. And then because we're doing a full power flow here, we can get ratings like maximum branch ratings, voltages, things like that. But because we're really stressing this grid, a lot of times we're taking out more than half its transformers. Not unsurprisingly, some of the power flows did not converge. So in this case of running 500 contingencies, about 22% did not solve. So with this approach, because I'm using an existing contingency analysis package that has lots of details, if I want to know what goes on in any contingency, I can get lots of details. Like PowerWorld has this functionality where if you click on the contingency, it tells you what occurred. The key takeaway from this is I did not define anything for these contingencies. What occurred is auto inserted by the process of doing these stochastic power flows. If I make a summary of the results, this is a histogram of the 500 contingencies. If I look at how many transformers failed, on average, it's 7, and that makes sense. If I've got 14 transformers, then 50% of the time they're going to fail, and 50% they won't. On average, 7 are going to fail, but you get the outliers. Sometimes you get only 2 failing, sometimes you get 12 failing. And then you can rerun the contingency if you want. And when you rerun it, there is actually an option, it's given right here, on whether you would like to reset the stochastic random inputs. And this functionality is really nice when you're trying to compare what would happen if I changed my PFW model. And we'll get to that in just a second. If I reset it, every time I rerun the contingency analysis, I'm going to get a different result because I'm dealing with stochastic models. If I toggle this flag to no, then every time I rerun contingency analysis, I'm going to use the exact same random inputs. Usually, of course, you wouldn't want to do that unless you're changing something. And in the example, as we go forward, we're going to be changing the PFW models. So rerunning the contingency analysis 4 more times with the random variables reset, I get 102 power flows that didn't solve, 111, 123, and another 111. And that, recalling the initial value was 112. The conclusion is that about 22% of the time, this case is not going to solve. So if this were a real system, of course, it's not a real system and it's not dealing with a real input. But if it were, if that earthquake were to occur 22% of the time, I probably would have a system-wide blackout. Okay. But then, 80% of the time I would. If I don't reset the values, I continually get the same input. And why I want to do that is perhaps I want to address the question of how does the number of unsolvable contingencies change if the resiliency of some of the transformers is improved. So the idea here is we're dealing with a planning tool, and in a planning tool, you want to make things better. So you look and you say, okay, what should I improve? And one hint on how you might want to improve the system is when you do the stochastic study, 500 contingencies here, it can actually, we've got a value in there that tells us for each transformer in the system, how many times that transformer was associated with a power flow that did not solve. And some transformers are associated with a lot of power flows that didn't solve, and some transformers are associated with less. So it would kind of make sense that the transformers that are most associated with the power flow not solving would be the ones that you might want to strengthen. And to make it easy to model strengthening of transformer, you could either go through and change your piecewise linear fragility curve. Essentially, you'd be pushing the curve to the further to the right and further down, or we've actually added some scale parameters that make it easy for testing purposes, design purposes, to just shift the curve. Here, I'm just shifting the curve over to the right by a PGAG of 0.5, so it makes it more durable. When I do that, I decided I would strengthen the four transformers that were most likely to be associated with unsolvable power flows, and that was a 345 to 138 one here, two 345 to 138 ones there, and the 138 to 69 there. When I did that, I reduced the number of unsolvable cases from 112 to 40. So this provides me with kind of a quantifiable way to say, how does improving transformers increase the resiliency of my grid? Okay, so the next example is on a 993 bus system. This is one that it's a synthetic grid, so it's all fictional. And we deliberately located it in the New Madrid seismic zone, which is the kind of the bullseye that I showed you on the map earlier. Technically, it's ground zero is kind of in the Missouri Boot Heel region. That's a part of Missouri that sticks down into Arkansas. And about 220 years ago, they had a big earthquake there that had a magnitude of up to about 8.2. And if Memphis has existed, Memphis did not exist at the time. Memphis would have had a shaking of a Mercalli level of 9, which is equivalent to what Mexico City experienced in 1985, which caused a lot of loss of life. Okay, so what I did is I took the PGA data from the earlier figure, and then I used the same fragility curves as before. This is the one line for the case. The green arrows are kind of showing the flow of power. This is the input that I used. I assumed the PGA value at the location just based on what was coming off of the map there. And here, this is the Boot Heel region. There's high values there. This is Memphis down here. In this data set, Memphis is just seeing 0.15, which is much lower than what the level 9 would indicate. Level 9, I think, indicates 0.75. And then this visualization is a geographic data view where the size of the ovals indicates the transformers in the case, and then the the size of the oval is proportional to the megawatt flow through the transformer. So you can kind of see where the heavily loaded transformers are. Um, this second GDV, it's the same data as before. It's just they used a geographic layout algorithm to kind of spread things out to show you that in some locations like Memphis, there's actually a lot of transformers there. You just can't see them because they're kind of geographically on top of one another. When we did the analysis, I ran 500 Monte Carlo contingencies. This is the histogram of how many transformers failed. Fewer transformers failed, about 12% failed now, but it was still a lot of transformers, and it still resulted in about 38% of the power flow cases not converging. So the takeaway for this synthetic grid is if an earthquake with that input set occurred, likely we would have lost the entire 1,000 bus case. Of course, the challenge for us is because the Memphis region is part of the Eastern Interconnect. The question is, would that have caused the propagation uh, to cause a much larger blackout? And that's something that we're going to be considering going forward. Okay, kind of wrapping up here, additional PFW models. There's lots of different models that could be considered. I gave you some references on it. We are working on implementing that. In doing this, we also realized that we could actually set up PFW models that don't even have an external input, but rather they just change a model parameter. And this goes back to the original concept of a stochastic power flow in which you're just varying some power system parameters, say the load at the bus. To test that out, I took the 37 bus case and I set up PFW models that just varied the load at a location and tested out how resilient the grid was to load variation. Originally, I changed the load by 25% plus minus. So if I go to a location, this is one of the buses in the grid where the load is nominally uh, 21 megawatts. If you do a plus minus 25% variation, this is what I was seeing in the 500 contingencies. And I did that at every bus in the system. Now, this is the histogram of what's going on with the load. Because I was using a uniform probability density function for this, the histogram is pretty uniform. Now, because the variation in the individual loads were uncorrelated, the net system load is changing by much less. This is a 25% variation at the individual. No, this is actually 50% because they ran it at 25% and didn't see any violation. So I upped it to 50%. I finally got some violations, but they were still quite low. So this is 50% variation at each system. So I was really like shaking that grid around with respect to load variation. Because they're uncorrelated, the variation at the individual or for the system as a whole is much less because when it goes up at one location, it might be going down elsewhere. Uh, what we need going forward, and this is where input from industry can really help us out, is we need to figure out what data sets do people want to run for these external inputs. There's lots of data sets on earthquakes, so we kind of have earthquakes covered. You have the risk math, but you also have data from various earthquakes or projected earthquakes. So we've got lots of data there. We're working on trying to get ice storm data. And in talking with our utility partners, the question is, what do you want to see? Do you want us to set up a EXI data set for ice storm, thickness, accreditation, accretion throughout the ice storm? This is a graphic I found online. Maybe you want to do ash from a volcanic eruption. Maybe you want to do peak wind speeds from hurricanes. It's really trying to figure out what people want and then making sure that we can have the methodology to handle the input data sets. We don't necessarily need to know the data. We just need to know the format on the data so that we can load it in. Many future directions. We're working on developing new models. We need to know also. I mean, we've got a lot of good feel for how we should deal with the models. There's a lot in the literature already. We're working on supporting different data types for reading in the EXIs. If you work with weather data, being able to read GRIB and GRIB2 files is helpful. We're working with our atmospheric science people here to run various weather scenarios where they're using all their climate modeling methodologies to produce us data sets, either for historical events where we don't have good records, like we're looking at the 1899 cold snap that hit Texas, or projected future climates. For some like short duration EXIs, we're probably going to implement it in stability because when you have an earthquake, the time frame for the earthquake is similar to the time frame for stability. So this methodology could be directly transferred over into stability code. Then for the longer ones that develop over hours, perhaps, the question is, okay, how do we model something where it evolves over an hour? What do you do to represent that? Validation and machine learning, and we're certainly working with large language models, and we'll have more to say about that hopefully in the next couple months. So with that, I've got some time for questions here, and I think Victoria is going to read off the questions. And if you have questions, you can go ahead and type them into the Q&A.
All right. Thank you, Dr. Overbye, for the insight on an extensible approach for modeling the impact of deterministic and stochastic
Yeah,
external
you got it now.
inputs
That's good.
in the power flow and contingency analysis. So the questions that we have today, it looks like we just have one right now. It says, was there a significant increase in simulation time when including stochastic models?
Well, right. When you're doing a stochastic simulation, we're using a Monte Carlo approach here. So what we're doing is a whole bunch of power flows. So yes, it definitely scales up. The good thing with implementing it in contingency analysis is there's already good modeling methodologies for dealing with lots of contingencies. Utilities routinely run large grid models on thousands, if not tens of thousands or hundreds of thousands of contingencies. So doing a Monte Carlo run, yeah, it's going to scale just based on how a contingency analysis runs scales.
No. Oh, we got a couple more just now. Is there a way to backcast this for validation purposes using historical weather event data and historical load records from something like a historian?
Yeah, that's a great question, and we are actually working on a project with DOE to do that, where we're taking Uri data, and we have, of course, Uri, we had generator failures due to cold, so we are looking at validating that, and then because you have to set up these PFW models, and a lot of times, there's just not a lot of data, and the idea is that as you change things, like you winterize a wind generator, of course you're making it more resilient to cold weather. But yes, we are working on doing that. And the nice thing about once we do it with the Uri data is then, because we have access to ERA 5 data going back to 1940, we can play in other weather sets as well. For example, we're working on right now, we're working on a paper where we take the coldest weather College Station has seen since 1940. That occurred in 1949. I think it got down to like -3 degrees here. And we are saying, well, how would the grid respond to that weather condition? And uh, that'll be interesting to see. Now, the difference between the 49 event and Uri is in 49, the cold weather did not cover the entire state. It was actually mostly in central, well, our part of Texas, Austin, College Station, but north of here and south of here it was warmer. So we don't think it's going to be as bad as Uri, but yes, we can do that. And we're working on doing that.
All right. Can you use a standard set of contingencies, but use a stochastic variable for load and generation output?
I yes, you can. That's a really good question. The methodology totally supports it. Um, it's a question of saying, okay, if I want to run like a standard contingency set where I have 100 contingencies, and let's say I want to stochastically vary the load, I can do that. And maybe I set up 100 identical contingencies and I apply my stochastic load to each one of those contingencies. So yes, an existing contingency will work just fine with these stochastic models. So we take the existing contingency, then we tack on additional ones. But to handle a lot of different deterministic contingencies, you would need even more stochastic contingencies.
Great. What are
One
the
one
typical
one one thing that I'm thinking about doing, I haven't done it yet, but like when we design voltage control in our synthetic grids, it would be nice to run a whole bunch of stochastic contingencies where we're varying the voltage set points on the generators by, let's say, 0.01 or 0.02 per unit and see how well the voltage control systems work. And that is something, all we need is a PFW model associated with the voltage set point on a generator. And since contingency analysis already supports that, that won't be hard to set up. And then we run it, and that'll help us a lot with resiliency and design of our grid. Or if you take a real grid and you do this, you'll get to see how resilient your voltage control system really is. So I think there's a lot of possibilities for uh, engineers to be doing this on existing grids.
awesome. So what are the typical failures of the transformers and how would the time to return to service affect the study?
Well, on an earthquake, there's a number of different PFW models out in the literature, and I have not done a lot of running of PFWs on transformers. So the answer is I don't know. I know PNNL has a nice report where they show a couple different transformer resiliency curves in there. Of course, at a particular utility site, you're going to have to know, what the resiliency of your transformer is. I should say with this DOE project that we are doing, there are about 30 other projects going on simultaneously. So we do quarterly reports, and at the quarterly report, we're hearing from the other projects, and a number of those projects are associated with earthquake resiliency. So people are taking transformers and putting on shake tables and looking at how they fail with the idea of making things more resilient. So I think as an industry, we're going to advance very rapidly. Our contribution to it is to provide a planning tool that can do the studies so the engineers can take the output of what another project might do, which might come up with a better fragility curve, and then look at the inputs, put the inputs into it and look and say, well, how likely is our grid to fail? Once a transformer has failed, how long it takes to restore it is kind of out of scope for our project. You're certainly not going to get it back in service for a long time. And as I said, a study that we're going to try to do very quickly is take like an Eastern Interconnect Dynamics model, and we have those models, and run that New Madrid earthquake on it to see whether we would get a cascading blackout occurring that could take down the entire Eastern Interconnect. That would not be a good situation.
Do we need to rerun the PF or can we use a LODF or PTDF based approach to recalculate the flows under different scenarios?
Uh, we've just implemented the rerunning the power flow. So I'm very familiar with the line outage distribution factors and the power transfer distribution factors. but we haven't looked into that. So here you're rerunning the power flows.
Okay. You showed results for transformers. What other components does the model support?
The model is supporting is adding models to support lots of different things. Transformers, transmission lines are something that we support. I mean, this is Power World version 25 code, which is at the beta stage right now. So we're adding more models kind of as we speak. But to take a transformer curve, it's the same underlying model, so it's also lines. So you can do lines, generators. Like we're setting up curves for generators for cold and hot weather resilience. Um, we're trying to figure out which other inputs to run. So we want to get data sets like to change the input on a transmission line failure from a earthquake to ice is not hard. You just need the ice data set, but it'd be the same general form of model. So I mean we are building up models rapidly. Think we've got probably about 5 different categories and maybe 15 models, something like that right now, but they're being added quickly.
Is there a way to include OPF in the Monte Carlo simulation method?
Yeah, the OPF is when you do a contingency, if you do the power flow, then you're running power flow. If you're doing optimal power flow, then you're doing optimal power flow. So in Power World, we've got the capability to run optimal power flows. I'm pretty sure we can run that in contingency. If not, it would not be hard to change.
Okay, for the larger synthetic power system used in the New Madrid example, I suspect that more than 500 Monte Carlo trials would have needed to be obtained at a high confidence level, i.e., 95% on the resulting histogram. Do you have guidelines on how to select the number of trials based on the established statistical research?
Right there, as the questioner mentions, there's a lot of work in Monte Carlo about how many simulations do you need to run for a particular confidence level, and the question is sort of confidence in what? Um, in what we're doing here, like with that, um, it's a 993 bus scenario. With that operating point, I think 500 contingencies is good enough to give me a good feel that says, about 38% of the power flows are going to fail to converge. And the way to test how good that is if I rerun the analysis, a different set of 500 contingencies, which is just clicking the button to rerun it, and that number comes out close to 38%, then I've got pretty good confidence that it's 38%. If it comes out at 30%, or 45%, then I have to decide, well, do I really care or not? And if I care, if I want to get it to a higher confidence level, as the questioner mentioned, then I'd have to do more. But I think how many are needed is dependent on what question are you asking. And what's being done here is a little bit different than what we do in traditional reliability analysis, where we might be looking at the 1 in 10 criteria.
Okay, this says, I'm assuming these results were from the repeated snapshot power flow solutions. Do you think a similar approach would be useful in QSTS or other time dynamics simulations?
QSTS. Is that what it says? I'm not familiar with that, but the answer is I don't know, I guess.
Okay.
Send
Um,
send me
in
send me an email and I'll be happy to address that.
All right, in your earthquake example, you considered a PGAG to be 0.5. Can PGAG itself be implemented as stochastic variable?
Right now, the answer is no. Should it be eventually a stochastic variable? I don't know. Maybe. But as a question notes, what we are doing is we're using stochastic models where the stochastic model has a random input associated with it, but the environmental inputs, the external inputs here are deterministic. Um, Whether we'd want to do that or not, I don't know. I mean, maybe we do, but we have not done that yet.
Okay, is it possible to run the external inputs of that earthquake in a real world case to see how often a blackout would occur?
Yes. Do we want to do that? Yes.
Oh, and it looks like Thad answered that it would be quasi static time series is what that meant.
Oh, yeah, we haven't done it with time series. We do have a time series analysis here. In answer to the previous question, where can we take a real grid and run it? Yes, we can take a real grid and run it. We have like the Eastern Interconnect model, or we can make an equivalent, and we can run it on that data set, no problem. The challenge is what sort of fragility curves do we use? So if we were doing a study, like let's say one of the utilities in that area asked us to do a study, we would say, well, what fragility curves do you want to use? I know from some of the earlier work that I've looked at, like the PNNL report, for different classes of devices, they do have different fragility curves, and that would just be generic curves. So that would be the next step is to say, okay, for a 500 kV transformer, we're going to use a different fragility curve than for, say, a 161 kV transformer, 161 kV high side transformer. But that would be the sort of analysis that we would do. It's like, yeah, we'd be very interested in doing that. We haven't done it yet, but we probably will. Of course, if we do that, we're probably not going to report the results because there'd be too many assumptions in it. But we can certainly work with utilities to do those studies.
All right, well, I think he has covered your last question. Thank you, Dr. Overby, for this insight. And thank you for your active participation from all participants, and thank you for attending. Please be looking for upcoming webinars and events on the Smart Gridder website at smartgridcentertamu.edu. That's
Thank you.
smartgridcenter.tamu.edu.
Okay, thanks.
Thank you.
And Victoria, I'll